Okay, let's take a simple heating example here. So let's say we have an air handling unit that has a heating coil in it. So we're going to take 700 meters cubed per minute of air that comes in at 4 degrees C, 80% relative humidity. We're going to heat that air up to 45 degrees C. Our questions are, what's the relative humidity of the air coming out of this air handling unit? And how much heat do we have to provide? What's the rate of heat input in order to achieve this? So first thing we would do, write the I guess we can plot the points to find the relative humidity at 2, and then we'll apply the conservation of energy to find Q in. So let's find our points here on the psychrometric chart. Number 1, we've got 4 degrees C. So here's 5 degrees, 1, 2, 3, 4, and 80% relative humidity. So there's 10%, 20%, 30, 40, 50, 60, 70, 80. So point 1, right there. Then there's 90%, 100%. So there's 1. As we heat the air, we're not adding any moisture, we're not taking any moisture out of the air. So the humidity ratio cannot change. Since we're not inputting any water, we're not taking any out. So the amount of grams per kilogram of air must remain constant at, let's see what this is, at 4 grams per kilogram. And so as we start to heat the air, we're just going to go along a horizontal line. Constant humidity ratio until we reach our exit temperature. So let's see, now we're up in the 30s, we're at 40, we need to get to 45. So 0.2 is going to be right there. Okay, so first thing we want is the relative humidity at 2. So we can see we are lower than this 10% relative humidity line. And then from what I described earlier, no humidity would be 0% relative humidity. So 0 on humidity ratio. So it looks like we're closer to 10 than we are to 0. I don't know, you call that 7%. Something like that, less than 10%. This is why a lot of times in the winter, even if it's cold and wet outside, it might be raining, 100% relative humidity, you still feel dry because you're taking that air from the outside that doesn't contain much moisture as far as grams as humidity ratio. Now as relative humidity is high, but humidity ratio is low, then we heat that air up, now it's very dry. Its relative humidity is very low. Normally, humans, people like to be around 50% relative humidity, maybe 25 degrees. That's a lot of times what you're shooting for with your conditioned space. Okay, so we've got the 7%. Let's write the conservation of energy now. If we write energy balance for this, we have heat in plus the mass flow rate times the energy entering at 1 minus the energy leaving at 2, and that equals 0 if this is a steady state system. So we want to know Q. So it's going to be the mass flow rate times H2 minus H1. We can get H2 and H1 because we have those states defined. We have points on this chart where we can read those enthalpies. The only thing we're missing is the mass flow rate. Mass flow rate is volume flow rate divided by specific volume. We've got the volume flow rate, 700 meters cubed per minute. A lot of times in this industry, flow rates are specified in terms of volumes. There are certain codes and regulations where you have to supply a certain amount of air or fresh air in CFM or meter cubed per minute to a conditioned space. And then the energy balance obviously depends on the mass flow rate, so you've got to find the density or specific volume. On the psychrometric chart, we've got the specific volume. So if we come down here to 0.1, because that's where 700 meters cubed per minute is, we find that our specific volume there is right on this line. So here's 0.8, here's 0.78, so that one is 0.79. See the 0.78, 0.8, 0.79 is our specific volume at 1. So if we find the mass flow rate now. Meters cubed per kilogram. So meters cubed cancel, kilograms go to the top. Actually, I want to do one more conversion. So we're going to want kilowatts for our heat rate. So let's get from minutes to seconds. We've got minutes on the top, so 1 minute is the same as 60 seconds. Let's calculate that real quick. All right, so our mass flow rate is 14.77 kilograms per second. Okay. Let's see, now we need Qn. H2 minus H1. Here's 0.2. These lines of constant enthalpy, here's 50. Here's 60. So we can see we fall in between those two. That's more or less halfway. I'm going to call it closer to 60 than 50, so I'll call it 56. And at 0.1, here's 20. And here's 10. So about 14. Calculate that. $56, 14, you get 620 kilowatts. All right, simple heating. Key thing here is the humidity ratio doesn't change because we didn't add or take away any moisture. So that number of grams per kilogram of moisture cannot change.